Hi, I'm Aparna Narayanan, and this is my project for the course EEL6825 Pattern Recognition. The title of the project is Analysis of Rhythm for Beat Detection. This project is about detecting beats in an audio track, and beats, as we all know, refers to the pace of an audio track. Recognizing beats in a song is something that occurs very intuitionally to us as humans, but the same cannot be said for software. Now, coming up with an algorithm that does the same detection can be pretty complex. And the main idea behind beat detection is to analyze a soundtrack and identify the fundamental period at which the beats occur. This would give us a BPM rate. Now, some of the applications of beat detection could be music categorization, where applications like Spotify that recommend music to users based on the current playlist or the current song could benefit from such an application. For instance, instead of recommending songs based on the genre of the current song that they're listening to, maybe the algorithm could use this BPM rate to determine and recommend songs to users. Because a user that's probably working out would be listening to a song that has a higher BPM rate, and it would be great to have an application that actually understands that the user is performing some kind of fast-paced activity, and hence that it should recommend a high BPM rate song. I'm now going to talk about some of the challenges in the area of beat detection and the main motivation behind this project. Now, songs or audio tracks consist of various components contributed by a wide variety of instruments, and there's no definite way to identify or single out a particular component or an instrument that contributes the most to beats in a song. It would also be inaccurate to say that a simplistic approach like probably summing up a subset of components would help us identify beats. It is intuitional to us as humans to recognize and identify beats in a song, but for software that reads music as a composition of different components, it needs the right support and algorithm to be able to do the same data processing that we are able to do. Even though we don't realize it, the human auditory system does a lot of complicated data processing to be able to recognize beats. Now, the main intention is to be able to mimic this capability in the form of software or an algorithm. And that is the main motivation behind this project. That is to be able to model this human ability to perceive beats in the form of an algorithm. I would now like to focus on some of the existing approaches in the area of beat detection. In this particular paper, that is Music Understanding at the Beat Level, the author demonstrates an algorithm that combines some low-level signal processing and uses it in combination with pattern recognition to recognize beats in a song. The author extracts drum patterns from a song and uses template matching to determine beats in this particular algorithm. The system runs on a real-time parallel processing system, and the main focus is on audio tracks with drum beats. In this paper, the author introduces a technique called as beat spectrum, where the analysis of tempo is represented in the form of a beat spectrum. Well, peaks in the spectrum represent major rhythms in the audio, and the lag time of each peak is said to represent the repetition time. The author basically provides a graphical way of representing rhythm variations over time, and he does not rely on specific features like energy peaks, but relies on repetitive information in the source audio. I'm now going to provide a brief overview of the algorithm and then delve into details of each of the stages in the further slides. So the main idea behind this algorithm is to find occurrences of sudden impulses in an audio track and identify the rate of these occurrences. According to most research in the area of beat detection, the best way to analyze a soundtrack is to first split it into its various frequency bands. So in order to do this, I have converted the signal to frequency domain and divided the spectrum into subbands. Any further processing is then done on these subbands and then combined together. The next stage is to use differentiation to recognize any increase in amplitude. And the final stage is to use various comb filters which are convolved with the original differentiated signal. And the comb filter which uses the highest energy is identified. And this would help us identify the tempo of the audio track. In this stage, the spectrum is split up into its various subbands, and this can be understood to have the effect of separating various instruments in a musical piece. So algorithmically, first the FFT of the signal is taken, and then I've assigned appropriate chunks of the signal to various subbands. As per the recommendation of some of the authors, I have selected the subbands and specified it here. Finally, in order to get the time domain signal, inverse FFT of the signal is taken. Since we're interested in recognizing beats in an audio track, the main idea is to identify segments of the audio track where there's a sudden change in amplitude of sound. So in order to do this, we first have to reduce the signal to its envelope so that we retain just the important information that we're looking for. We use low pass filtering, that is full wave rectification is done first on the signal, and then it is convolved with the right half of a Hanning window or a half Hanning window. This would then give us a smoothened envelope signal. We can differentiate the envelope signal to emphasize on a change in amplitude. Largest changes in amplitude correspond to beats because beats are simply a periodic emphasis of sound. This differentiation stage is then followed by a half wave rectification so that we can only see increases in sound. This is the final stage of the algorithm where a comb filter is used. A comb filter is basically a series of impulses that occur periodically with a tempo that you specify, and convolving various filters with the differentiated signal will give us an output, the energy of which would be highest when there is a match in tempo. Now, this is mainly because convolving a signal with a tempo matched comb filter will give us an output which is an echoed version of the original signal. Now, this overlap of peaks that occurs while convolving will result in an energy which would be higher. In the algorithm, first the FFT of the frequency banded signals are taken and they're multiplied with the FFT of comb filters. Now, energy of each resultant signal is taken, and for one given tempo, all the frequency subbands resultant signal energy is added up, and whenever the energy peaks, that particular tempo is recognized as the correct tempo of the song. I'm now going to show you a demo and the working of the code. So the very first stage of the algorithm is the frequency splitting stage, where I read the audio signal and then I segregate the signal into its respective subbands. So first the audio signal is read here using the audio read function, and then I convert it into frequency domain by using the FFT function. Then I split up this FFT signal into its respective frequency band to finally give an output which consists of multiple columns where each column represents a different frequency band. And here I'm plotting the signal. I'll now demonstrate the output. This is the time domain representation of the song, which is Limp Bizkit's Rolling, and this is the frequency domain representation of the same song. The next stage is the smoothing stage, where the audio signal is read and the envelope of the signal is extracted. So I start with creating a half Hanning window in this section, and then I transform the audio signal to time domain. After that, it's followed by full wave rectification, after which I've converted the full wave rectified signal into frequency domain. Now, the full wave rectified signal has to be convolved with the half Hanning signal which I'd created earlier. So convolving in time domain is equal to multiplication in frequency domain. So multiply the two signals to get the filtered audio output, and that I've converted used inverse Fourier transform to get the final output in the time domain. I'll run this and demonstrate it. So this is the waveform that represents the envelope of one of the frequency bands of the audio signal. The next stage is the differential stage, where the audio signal is differentiated to obtain changes in amplitude. So here I find the difference of consecutive samples and store it in diff, and this is followed by half wave rectification, where only those changes that are positive are retained in the output. The output is a time domain signal, and I can demonstrate the plot here. So this is a signal this is a waveform which represents changes in amplitude. This is the final stage of the algorithm where a set of comb filters are convolved with the audio signal, and the one with the highest energy is said to be the correct tempo. So I have a range of tempos here for which I'm using comb filters and convolving it with the audio signal, that is 60 to 240 is the range. So the first step in the algorithm is I convert the audio to frequency domain, and this is the frequency domain audio signal. And for BPMs ranging from min to max, I create a comb filter here and convert the comb filter to frequency domain, and then convolve that comb filter to the audio signal and calculate the energy. Now for a given tempo, the energy is the sum of the energy of all the frequency subbands which I've considered, and that would be the total energy for that particular tempo. Now if that energy is the maximum energy amongst all the energies computed till now, then the BPM is said to be the correct BPM, which matches with the tempo of the song. So I've created a plot of this, and also will obtain the output in the form of a variable which I can demonstrate. So this is the plot of the energy of each tempo versus the BPM of considered for the comb filter. So you can see that the peak value occurs at a BPM of 97, and hence 97 is said to be the correct BPM for this particular song. Thank you. On doing a performance evaluation of the algorithm, I found that it is quite accurate in detecting the BPM rate for various songs. One of the drawbacks is that it assumes constant tempo throughout the song, because I use a 3-second sample for evaluation, so it does not take into consideration the possibility that the song could have variable tempo. And it also does not work for songs with a weak tempo, that is when there isn't much support from other background instruments for the tempo. It does not work very well. And also the comb filter stage, which involves convolving various comb filters with the original voice signal, can be computationally intensive. In conclusion, I found that this algorithm successfully detects beats and provides an accurate BPM rate. Some of the improvisations that are possible is that it can be made to work with longer samples by improving the processing speed, and also that extensions can be made so that the algorithm can include harmonics in music. Thank you.